and we're going to talk about graphs of different functions. So first thing we're going to start off with is a constant function. And a constant function, if you notice, the graph looks like this. Okay, it's a straight horizontal line. And the function for this line is f of x equals 2. So how is that a horizontal line? Well, think about it. That's the same as saying y equals 2. So what is y when x equals 0? 2. When it's 1. When x equals 1, y is 2. When x equals 2, y is 2. If I were to plot those points, it'd look like this. Right? And I could say when y is 3, when y is negative 3. And if I connect all those dots, I would get my straight line constant function, which is f of x equals 2. If I wanted f of x equals negative 3, well, when x is 0, y is negative 3, and so on and so on. So again, I would have a horizontal line. Okay, this line is f of x equals negative 3. Okay, it's just always negative 3. That's why it's called a constant. All right. Now we have something called the identity, which is f of x or y is equal to x. So when x is 1, y is 1. When x is 2, y is 2, and so on and so on. That's why it's called the identity. And you notice it's just a diagonal line. It goes through 0 because when x is 0, y is 0. And it has a positive slope of 1. Remember, a line is y equals mx plus b. So here our b is 0. That goes away because it hits the y-axis at the origin. My slope is 1, which gives me my x value. Okay. Now, absolute value it looks like it's maybe hard to remember. And really, if you remember, the absolute value of x means that no matter if x is positive or negative, y or the output is always positive. So if we look at our just y equal x line, let's just say we start with our y equal x line because it says absolute value of x, so it should look somewhat like x. And all the negative parts, all this part right here, basically flips up across the x-axis because all these values can't be negative, they have to be positive. We can see that if we flipped it up, it would go along that line. Okay, so that's why it looks like a V. Then we have x squared. This is called a parabola. And it's just a U. Goes through the origin when x is 0, y is 0. When x is 1, y is 1. And also when x is negative 1, y is 1. This is still a function because it passes the vertical line test. Notice the next one is x cubed, and it can have negative y values. So if I were to say this is x cubed, and look how similar it would be to make this an x squared, because all these negative values of y down here have to flip up, and it looks a lot like a parabola, especially if I drew it better. So that's why sometimes things are able to go below the axis and be negative, and sometimes they stay positive because x squared is always positive. Square root, well, the smallest value the square root can be is 0, which is why it starts here. Okay? Because we can't take the square root of a negative number. And then it slowly increases. Okay? Like the square root of 1 is 1, but the square root of 4 is 2. And the square root of 9. So we'd have to go all the way out here to 9 so we can move up 1 more. So we're moving 5 more places to the right. Let's say here. And then we can say, okay, now it's 3. And so slowly it's increasing, but not quickly. Cube root of x. And it looks similar to a square root, except you can have negative values for the cube root. Hence, we have our left tail that continues from. So if this was a cube root, it would be very similar, and then it would go like that. And now it almost looks exactly like the cube root. Okay? The same thing is happening with this next function. We have a reciprocal function, which looks like this. And if we square x, notice we can't have any negative values for y. So this piece right here flips up like that. And now it looks very similar to 1 over x squared. So these are the really important, let me see if there's any more else, other ones down here. No, these are the really important graphs that you need to know. Then what we were going to do is talk about the domain and range. And what I'd like to do is go back and talk about the domain and range for each one of these functions. Let's look at the constant function. The domain, well, the domain are my values that my input variable can be. And in this case, we'll just call it our x values because we're using x. So this is my x-axis. And as you can see, there's no real reason why it can't go from net to negative infinity or to positive infinity, because f of x equals 2 no matter what. So my domain is going to be from negative infinity to positive infinity. And this is interval notation. We're going to go over interval notation in just a minute. Infinities are always parentheses because we never can get to infinity. I can't actually plot infinity. So that's really all that I can do. And my range, I could say my range is from 2 to 2, including 2. Or I can say it's the number 2. The first one would be more interval notation. I'm starting at 2, I'm ending at 2, and I include 2. That's why I have those square brackets. And that's the only number that it can be. That's the only number that my y value or my output can be. Let's look at our identity. My domain, well, it's going to go on indefinitely. Well, let me show you. This is going to go on indefinitely in this direction. This is going on indefinitely in both directions again. So, and there's no reason why there's no problem with any value for x. X can be anything. So again, this is from negative infinity to positive infinity. But my range is going to be different than it was last time because it's going to keep going down into negative infinity, and it's going to continue up to positive infinity. So my range here is also going to be from negative infinity to positive infinity. Then we look at our absolute value. I'm going to make this a little thinner again. Okay, so we look at our absolute value. Again, my x value goes on indefinitely in both directions. So my domain is going to be from negative infinity to positive infinity. But here, my range, when I look at my range, let me see if I can, let's see if this will help. So if I were to drag this ruler here, look at when we start having a value of y. Nothing, nothing, up right here. So starting at 0 and including 0, forever until infinity, we can see that we have an output. So we would say our range starts at 0 and ends at positive infinity. Let's look at our next group. Similarly, if I did the same thing here with my ruler, if you look and see when the function starts, there's no part of the parabola anywhere down here. But once I hit 0, from then on, there's values. There's output values. There's y values. So my domain is, and it's going to go on indefinitely in both directions. And if we also can look at our functions themselves, we can see that there's no restrictions on x. X can be anything you want. So the domain is from anything from negative infinity to positive infinity. And my range is starting at 0, as I just showed you, and going to infinity. Okay? So cubic function, domain, still no issue. So we're going from negative infinity to positive infinity. And my range is also negative infinity. Notice this is going on indefinitely in both directions. Negative infinity to positive infinity. Now we have a different situation. So if I talk about my domain, and I'm going to really keep using this ruler for a little bit. I know some people really have a problem with domain and range. So I'm going to try to show you. I'm making it vertical because notice I'm going across the x-axis. So where does this graph start if I look across the x-axis? Oh, when x equals 0. So I can say this goes from up, but I do include 0 because the square root of 0 is 0. And I go to positive infinity. And then if I look at the range, I'm looking at my y values. So I'm going up until I get to 0, and then that goes to infinity. So my range also is from 0 to infinity, right? And let's look here. Well, the cube root, as you can see, I mean, this is really, you have to remember these are continuing. There's only so much space that they're being given, but they continue on forever. So we look here and we can see that our domain, well, actually, we don't even need the ruler for this. Our domain starts at negative infinity, comes through and goes to positive infinity. And our range is the same. This is going to continue down. We just don't see it because it's going down at a slow pace, but it can go from negative infinity all the way to positive infinity. Now the reciprocal is a little different because notice if I look for my domain, we have values all the way here, but we have a situation, okay? You can't really see it, and I don't know if you remember hearing about it, but there is an asymptote at x equals 0. It cannot touch 0. So let's write it down and then we'll look at the actual function to see why. So my domain is from negative infinity to 0 union, which means I combine two different, it's like kind of like a plus for intervals, plus I'm going to start at 0 and go to infinity. Now, because I have those parentheses instead of the square brackets, it means it's not including 0 in either way. So it's like we're coming all the way up to 0, not including 0. And then we're starting right past 0 and going all the way to infinity. Why is that so? If you look at your function, we're not allowed to divide by 0. So we have to make sure we take out that 0. Okay? Now let's talk about the range. The range is going to negative infinity. I mean, it's starting at negative. And we always, so whenever we're using interval notation, and we'll talk about this again in a minute, we always start at our smallest value and go to our largest value. If you do it the opposite way, it's wrong. Even if you have it right, like if you said from positive infinity to negative infinity, that would be incorrect. We always go from our smallest number to our biggest number. So our range is definitely going to negative infinity. And then it's coming up. And it looks like there's something else happening here. That's because this function cannot equal 0. So it's going to 0. We're going to union it because then it starts again after 0 and goes up to positive infinity. So why does it do that? Well, let's say y can equal 0. I would have 0 equals 1 over x. I could solve this. I could multiply both sides by x, which would be 0 times x equals 1 over x times x. This x would cancel with this x and give me 1. And notice I would end up with 0, because 0 times anything is 0, equals 1. Well, obviously, that doesn't work. So we can say this function is never going to equal 0. So that's why I know my range is from negative infinity to 0. And then I'm going to add on to that 0 to infinity. And then the squared, again, very similar. Let's get rid of this ruler. I think we got the picture. Our domain, well, it's going from negative infinity. And for the same reason, x can't be 0, x squared can't be 0, because we can't have it 0 in the denominator. So we're going to go all the way to 0. We're going to stop. We're going to pick up again right past 0 and go to infinity. And my range, well, we have no negative values. We know from the reciprocal function that it can't equal 0. So we put an open parentheses or a parentheses 0 to infinity. And that's my range. Because I start just past 0 and I can go all the way up to infinity. These two lines continue upward. Okay. Now let's just read what it says about the domain range. The domain is the set of possible input values to a function, and the range is the set of possible output values of a function. So basically, the domain is really the set of all values that I can put into this function. If you think of a function, let's do this. Maybe this is helpful. If you think of a function like a machine, right? So let's say we have a car. Okay. Well, that's a pretty bad car. Could have made it a truck, maybe. Let's say it's a car. And we're going to input something and we're going to output something. Okay. So we want to know what the set of all the possible inputs are that I can put into my car. If you were just talking about the car itself, what could you put in? You could put oil, gas, other kinds of fluids like washer fluid, transmission fluid, brake fluid, many different kinds of fluid. Okay. Now, I could say my domain is fluids. But would that be really true? Well, can I put Coca-Cola in my car? Is there a place I could put it where it wouldn't hurt it? No. So I wouldn't be able to say fluids. I'd have to be more specific. I'd have to say, well, I would have to actually give a list because there's so many kinds of fluids. I could say water goes in my car, but any kind of water? No, I can't put ocean water in my car, even if I put it in the right place where water goes, right? Because that would hurt my car. So the domain is the set of things that you can put into your machine. And what's our output here? Well, hopefully our output is go, right? The car moves. So this would be my range. My range would be go. And my domain would be oil, gas, water, and other fluids that go in the car. And we would call that our domain. What goes in and what comes out. I don't know if that helped, but if it did, great. If it didn't, ignore it. We're going to talk a little bit more about interval notation. So interval notation is a more compact alternative to inequality notation. Inequality notation is like x is greater than 3, x equals 5, something like that, right? In which intervals of values are referred to by the starting and ending values. So when I talk about an interval notation, why we're calling it interval notation, because I have a starting point, I have an ending point, and I know that every single number in between counts. And could you really, you couldn't write x equals 1, x equals 1.01, x equals 1.001, x equals 1.0001. I mean, you'd have it. There's infinitely many numbers between any two values. So we can't really write it like that. We could write it in inequality notation where we say, well, it's between 2. It's going to be between 2 and 3. We can say that, right? This would get every number between 2 and 3. But we really like this interval notation, okay? So the curved parentheses, like I was explaining as we were kind of going before, are used for basically strictly less than or greater than. Okay, so what does that mean? It means that we don't really, all we really want to think about is what the beginning number is, what the end number is, and am I including the beginning or the end? That's the only way I'm changing my parentheses. It's curved. It's going to be, I wouldn't say strictly less than, but it could be less than, or it could be greater than. And my square brackets are for, so square brackets would be for less than or equal, greater than or equal, because we are including that point. Since infinity is not a number, we can't include it in the interval. So we always use the curved parentheses with infinity or negative infinity. I didn't actually leave the table. I think the table is, it's in your book, but I think it's more confusing than it's helpful because interval notation is really simple. So I'd like to show you how to make it simple. So I look here and I want to describe the interval of values shown on the line graph using set builder and interval notation. Let's start with interval notation. So interval notation, I'm going from 1 to 3. And oh, I'm including 1, so I put a square bracket, and I'm including 3, so I put a square bracket. Over on this part of the line, I'm going from 5, and notice I have this arrow, which means it just keeps going forever, so I'm going to infinity. Now, I have this open circle, which means not including that point. So if I don't include it, I use the parentheses, and always parentheses for infinity. And then I put a U between them to say, let's unite them. Let's bring them together and make it an interval. Set builder notation would look like this. First, so this is interval notation. Set builder notation looks like this. We have parentheses. I'm sorry. We have these curly braces. These curly braces, whenever you see them, almost always mean that it's a set. Okay? So whatever goes inside that, it's a set. So we have a set of, and we're going to say this, we're going to say this is an x-axis. So we're going to say the set of all x values such that, this means such that. And now I would put my interval. So how would I do it? Well, I'm going from 1 to 3. So I'm going from 1 to 3. In between there's values of x. And I can include 1 and I can include 3. So I have an interval that says here, x is between 1 and 3, including both 1 and 3. And then that union, if I put it in set builder notation, would actually become an or. And I think I probably have to erase this and move it out a little bit. Or now I could say x is greater than 5 because I'm not including 5 and I am saying it's every value bigger than 5. So it would translate to this. The or basically translates from the union. And everything else here, you know what? So this doesn't get confusing, I'll say such that it's not a 1, it's just a straight up and down line. All right. Now, let's look at how to find the domain. And most of the time when we don't have something on a graph, we don't look for the range. It's a little more difficult to find the range of things than the domain of things. For example, for A, just like when I was trying to show you that car, I can't really put every fluid into that car, right? I can't put wine in it. I can't put vodka in it. I mean, I could, but I'd probably ruin my car, right? So the same thing is true for these functions. We want to find what values we can put in for x so that I don't blow up my function. I want my function to actually give me some type of output. So I look at this and I say, well, x can't really be anything because if x makes this number under the radical negative, I can't find the square root of a negative number. I can find the square root of 0. So that's the smallest value. Remember, we saw that on the graph as well. But this says x plus 4, not just x. So what I want to do is I want to start with x plus 4 is greater than or equal to 0. Because I know that whatever's under that radical sign has to be greater than or equal to 0. And now I can just solve it. I can subtract 4 from both sides. And I have this cancels and I get x has to be greater than or equal to negative 4. So let's look. If x is negative 4, yeah, that's 0. So the whole thing becomes 0. If x is negative 3, sure, then I have the square root of 1 times 2 is 2. But if x is less than negative 4, if x is negative 5, it won't work because negative 5 plus 4 equals negative 1. The square root of negative 1 is not a real number. So, nope, can't do it. So I can write this again in both. I'll write this as set builder and interval. Okay? So set builder notation would be x such that x is greater than or equal to negative 4. That's it. Okay? Interval notation would look like this. I can start at negative 4, I include it, and it doesn't have an ending point. I can go all the way to infinity, and infinity always gets parentheses. Let's talk about B. And I'm kind of always looking to see where is there going to be a problem? Like what values are going to give me a problem? So if I look at a fraction, well, what do I know is going to cause problems in a fraction? The denominator can never equal 0. We can never divide by 0. So like a little trick in case you forget is 0 over a number is good. But a number over 0, look what it says, no. Okay, sometimes people forget which is which. That's like a little trick actually somebody in one of my classes showed me, so I'll share it with you. So we can't have 0 in the denominator. So I just say, okay, well, 6 minus 3x cannot equal 0. And I can solve for that, right? I can add 3x to both sides. I get 6. These cancel. Cannot equal 3x. I can divide both sides by 3. And I get 2 is not equal to x. Or if you like it better, x is not equal to 2. Okay? So let's write it in set builder and interval notation. Set builder is the set of x such that x is not equal to 2. That's it. In interval notation, well, x can be anything but 2, can't it? So it could be from negative infinity. Actually, the best way to do this, here, let me explain the best way to do these. Because sometimes people get confused. So I always say, just draw a number line. 0, 1, 2, -1, -2. And I'm going to actually just draw above the line. So I have a hole at 2, and it goes to infinity and to negative infinity. And now, if you were to actually draw the number line, it would be much easier to see that I'm going to go from negative infinity, and remember, infinities always get parentheses, all the way up to 2, but I'm not going to include 2. But I'm going to start again right past 2 and go to positive infinity. So that would be the domain of B. So both of these are the domains of those two functions. And that concludes our first lecture from MAC 2233, section 1.1, and more to come. Thank you for watching, and if you have any questions, please feel free to let me know.